Welcome students. In this video, we're going to do 4 examples on how to use the thermal energy equation. This first example is an easy one on finding Q, heat. Let's get started. So to start with, we're going to read the problem and find out what our variables, our knowns and unknowns are, because it's a bit harder to draw a diagram for these particular problems. How much heat is needed to raise the temperature 500 grams of water from 20 degrees to 100 degrees Celsius? So we know the mass is equal to 500 grams. We know the initial temperature is 20 degrees Celsius. The final temperature is 100 degrees Celsius. And your formula sheet has the specific heat capacity for water, and that is 4,186 joules per kilogram degrees Celsius. Now the first thing you should look at in your table here is the units. We have grams, degrees Celsius, and joules per kilogram degrees Celsius. So we have a kilogram and a gram, which tells us we first need to do a unit conversion. Now we have 500 grams. There are 1,000 grams to a kilogram. So let's start there. I have 500 grams. My conversion factor is 1,000 grams, and that goes on the bottom because I want it to cancel with the 500 grams on top for 1 kilogram. So basically you're taking 500 and dividing it by 1,000, which gives you 0.500. We actually have a third zero there, kilograms, and that's our unit conversion. So our next step is to find an equation. Our equation for thermal energy is heat is equal to mc delta T, and delta T is our change in temperature. So we're looking for heat, we know mass, we know specific heat capacity, and we know change in temperature. So we don't need to do any changes to the equation. We can just sub numbers in. So we want to make sure we use the right mass, 0.5000, times by C, which is 4186. And our change in temperature is always final temperature, 100 minus initial temperature, 20. So that we can simplify, 0.5000 times by 80 degrees Celsius. And that gives us a final answer of 1.7 times 10 to the 5 joules. Now when you put that number into your calculator, you're going to get a large number of significant figures, but our question really didn't give us that many. In fact, the 20 is a counting number, so it would actually only be 1. In physics, we're not too concerned about the significant figures, but I don't need 6 or 8 significant figures in your final answer. So that's how you solve that problem. Okay, our second example, we're going to look at how to solve for mass. A sample of mercury is heated from 25.5 degrees Celsius to 52.5 degrees Celsius. In the process, 3,050 joules of heat is absorbed by the mercury, and we want to find out what the mass of the mercury is. So, looking at our knowns and unknowns, we have an initial temperature of 25.5 degrees Celsius, a final temperature of 52.5 degrees Celsius. Heat absorbed is 3,050 joules. Specific heat capacity for mercury is given to us, 140 joules per kilogram degrees Celsius, and mass is what we're looking for. So if we look at our units, degrees Celsius, joules, and joules per kilogram degrees Celsius. So no unit conversions are needed in this problem. We can get started with the equation. Our equation for heat, Q equals mc delta T, and we're looking for mass. So if we want to look for mass, then we need to bring these other two, C and delta T, over to the other side. And everything is being multiplied together on this side, so we just need to divide by C delta T on both sides, which will give us mass is equal to heat over C delta T. So now we have our equation and we can put numbers in. So I have mass is equal to my heat, 3050 joules, over specific heat capacity, 140 joules per kilogram degrees Celsius, times by delta T, which is 52.5 minus, because it's always final minus initial, 25.5. And I forgot my degrees Celsius. So we're going to do that first because it's a subtraction. So writing that out again. And if we do the subtraction, we get 27 degrees Celsius. Now the reason I wrote my units in here, I want to show you how this works. I have joules on top, joules on the bottom. Now there's a per here, so that means they're on the bottom. Degrees Celsius on the bottom, degrees Celsius on the top. That leaves me with kilograms on the bottom of this number, which happens to be in the denominator already. So that will give me kilograms on top for my final answer, which is exactly what I was looking for. So I put these numbers into the calculator. I'm going to get 0.807 kilograms for my final answer. And that's how you'd solve that problem. Okay. Example 3 says, what is the specific heat of a metal if its mass is 26.86 grams, requires 418.6 joules of heat to raise it from a temperature of 27.4 degrees Celsius to 67.3 degrees Celsius. So again, we start with our table of knowns and unknowns. The mass is 26.8 grams. Q is 418.6 joules. The initial temperature, 27.4 degrees Celsius. Final temperature, 67.3 degrees Celsius. And this time we're looking for the specific heat. Taking a look at our units here, Celsius, Celsius, joules, and grams. So they all look okay, except our specific heat capacity is usually given in kilograms. So let's convert that first to kilograms. And again, we divide by 1,000. So we'll just do that quickly here to get our new mass. Now we can put it into our equation. Q equals mc delta T. And this time we're looking for C. So we want the m and the delta T over to the other side. So we divide both sides by m delta T to give us specific heat capacity on one side and QMT on the other side. Putting our numbers in. Putting all those numbers into your calculator, you should get 391 joules per kilogram degrees Celsius. And that's how you would solve that problem. So here we have, if we have 200 joules of heat added to 25 grams of iron at a temperature of 15 degrees Celsius, what will the final temperature be? So looking at our knowns again, we have heat, which is 200 joules, mass, which is 25 grams, initial temperature is 15 degrees Celsius, specific heat capacity is given 450 joule per kilogram degrees Celsius, and we want to find the final temperature. So looking at our units, joules, grams, degrees Celsius, and kilogram. So let's do our quick conversion here. Again, dividing by 1,000 gives us 0.025 kilograms. Now we can put our numbers into, or find our equation. Q equals mc delta T. Now we want one of the terms of delta T. So we're just going to move the m and the c to start with. And again, they're all multiplied, so we can just divide them. So Q divided by mc is equal to delta T. Delta T is equal to the final time minus the initial time. So let's put that in there too. Q equals MC T final minus T initial. So now I know the initial time. I'm going to bring that over to the other side. It's subtracted here. So I have Q equals MC. To bring it to the other side, I have to add it. So I add my initial time, and that leaves me with the final time. So now I can put my numbers in and solve. Now you could do this in 2 steps. You could find delta T first and then just add afterwards too. That would work fine. So if I put the numbers into my calculator, I get a final temperature of 32.8 degrees Celsius. And that makes sense because it is higher than my initial temperature, and it tells me that heat was added to the system. So that's how you'd solve that problem.